Well, here we are back again, and this time we're doing an integration technique called partial fractions. And obviously there's going to be a rational expression, a fractional expression involved. And some of these are pretty straightforward. For instance, the one I've got here on the first screen. You come along, you say, geez, let's try a u substitution for the denominator. You take the derivative of your substitution and it equals the numerator. Geez, life is great. So you put your u in for the denominator. You put your du in place of the numerator, the 2x minus 1 dx. And although I didn't write it here, of course that integral is nothing more, nothing less than the natural log of u. And then you take and back substitute here, right, for your u, and you get the final answer, and there it is, and it's done, and life is good and beautiful. But you know, it doesn't always happen that way. That is, when you make a u substitution for the denominator, you don't get the numerator. So let's take a look at a problem where that's the case. So this time, if you allowed u, hypothetically, if u equaled x squared minus x minus 6, and you took a derivative, well, you'd get 2x minus 1, and there isn't a multiple of that would give you, it doesn't resemble 3x plus 11, nor does any multiple of it equal 3x plus 11. It just doesn't work. Now, if you knew, or if you tried to factor the denominator, and that's going to be the catch here, we need a factorable denominator for this method. If you factored the denominator and you could find the terms for the numerator, the problem would be quite doable. Now, right now it looks like magic how I got from the left side to the right side, but we can prove that it's true simply by saying, okay, that x minus 3 times the x plus 2 is a common denominator for those two fractions. And if I take the first denominator, it goes in that many times, and if I multiply by 4, I get 4 times x plus 2. And take a moment looking at it. If you cross the x plus 2's, you'd go right back to what you had. And that second denominator of that second term, doesn't it go into my common denominator exactly that many times? And won't I multiply by a negative 1? And again, if I took a look and canceled my x minus 3's from the second one, wouldn't I go right back to negative 1 over x plus 2? Now, take what I've got here with the common denominator and multiply out the numerator, and wouldn't you get 4x from the first term minus an x from the second? And wouldn't you get from the first term 4 times 2 is 8, and from the second, wouldn't you get minus a minus 3 or a plus 3? And wouldn't that be over my denominator when multiplied out? Isn't that x squared, doing the FOIL? 2x minus 3x would give us a minus x. Last times last would give us a minus 6. And wouldn't the total number of x's be 3x? And wouldn't the total of the constants be 11? And isn't that exactly what I started with? So we need a method to take this fraction, this big fraction, and break it. And we're going to call this method partial fractions. We're going to break this down into smaller fractions, because if we can do this, it'll mean that we can turn our ugly fraction, our big fraction, into two smaller fractions, and now we can integrate those smaller fractions, right? So let's take a look at a method. It's called fractional decomposition. And if you think about it, remind me tomorrow to tell you my joke about decomposition. So let's take a look at how this works. We've got this fraction, and I've put up the same problem. It's the same integral that we're working on. And remember, I talked about the fact that this will work when we can factor the denominator, and we want to completely factor it. Well, what we didn't know were these numerators for these partials. And these numerators will always be 1 degree less, so they will be constant. And there will be an a, or a constant, that will go with the x minus 3 denominator, and a different constant, well, it wouldn't have to be, but we'll label it b because typically it will be a different constant over the second term, if you will. So think about what that looks like, if we went right back and created that common denominator made up of the two partial denominators. Well, wouldn't our first denominator go in exactly x plus 2 times, and then wouldn't we take x plus 2 and multiply by the a, and thus we have a times x plus 2. And if we worked with the second term here, wouldn't we take the x minus 2, or x plus 2, excuse me, decide that it goes in exactly x minus 3 times, multiply the x minus 3 times the b, and we'd get b times x minus 3. And again, if you reduce those, you see you go right back to those two terms. So think about what's going on here in the numerator, and I think the quick, easy method for this, I don't know if you've seen it before, is consider the zeros, if you will, of the denominator. The zeros are 3 and negative 2. Let's put in a negative 2 and just see what happens. From the just working with the numerators now, because that's what we have to straighten out to find a and b. We know that the numerator has to equal 3x plus 11. Our partial numerator is this big quantity over here, right? A times that plus b times the other thing, right? That's what I've got over here. Well, if I put negative 2 in, one of the zeros of the denominator, won't I get 5 from the left side? And on the right side, won't my a drop and I'll get negative 5b? And negative 5b will equal 5 when b, of course, is 1. What's my other zero? Well, my other zero of the common denominator, the two factors in the common denominator, would be 3. So if I put my 3 in, on the left side here, I'd get 9 plus 11, or 20. And on the right side, when I put 3 in, won't the b drop, and I'll get 5 times a. And won't 5a equal 20 when a is 4? So you might have a slightly different way of doing that. That's sort of my way of doing it. We can talk about your way. But anyway, if we knew that, if we could recover our a and b, right, then we could take in this ugly, call it ugly integral. We could break it now into a difference of two integrals. We could make some partials, and then we could evaluate those separately and quickly come up with our answer. So let's try another problem, and this time we'll jump into one that definitely factors, and it has 3 factors. You can factor out an x. You see that the denominator is factorable to an x plus 2 times a 3x minus 2 Those are the three factors. The three factors are all linear factors, so we write them down below. And the numerator we'll write down as A, B, and C. So consider, if you will, that what we've got in the numerator on the left side is x squared plus 4. And on the right side, if we get a common denominator, and I didn't write all that out all over again, but you know, if we wrote them all out, the first one, the x would go in exactly this many times, and then we'd multiply it by the a. So that's what I have here, a times that. And then if we were to do it again, let me just switch up colors here again. If we were to take and put the second denominator into what is the common denominator, right, it would go in exactly x times 3x minus 2 times. So, and then I'd multiply that by the b. So that's where that 3x minus 2 times x times 3x minus 2 is multiplied by the b, right? And then finally, one last time, you know, how many times is that third denominator, 3x minus 2, go into the common denominator? Well, exactly that many times x plus 2. And then I'd take the x times x plus 2 and I'd multiply it by the c, right? So here is the x times x plus 2 times the c. I hope you're following all that. I hope that makes good sense. But now consider the zeros of the common denominator. Can you see that you have 0? You have 3 of them. You have 0, negative 2, and 2/3 from the third one. Notice what happens when you put 0 in on the right side. Well, this term, the b term and the c term drop away because it's 0 times c is 0, and 0 times the rest is 0, and 0 times b is 0, and 0 times the rest is 0. So all you have is 2 times a negative 2. That's a negative 4a equals 4. That suggests that a is negative 1. And then do it again. Do it again with the next 0 of the common denominator. If you put it in the right side of the equation, won't you get 4 plus 4 or 8? And then if you put negative 2 into this term, it would go away, right? Negative 2 in the middle term produces b times negative 2 times a negative 8. And if you put negative 2 in this third term, well, it goes away because negative 2 plus 2 makes for a 0 factor. So you end up with negative 8b's equals 8, positive 16, I don't know how I got negative 8, positive 16b equals 8. B must be a half, right? And then come at it one last time, and again, I hope you're following all of this. If my 0 of the common denominator is 2/3, and I put 2/3 into the second term or the first term, both of them go to 0. The only one that lives is the last one. So I'll get c times 2/3 times 2/3 plus 2. And 2/3 plus 2 is 2/3 plus 6/3, or 8/3. So there's my 8/3, my 2/3, and my c. And you know, what have I got? Well, I've got 16 over 9, right? And if I multiply, you know, both sides by 9 over 16 to get c, the 9's will cancel, right? I'll get 40 over 16, which reduces, 8 goes into both, reduces to 5/2. So after all of that, I get this fairly complex function here, this rational function. I get it stretched to 3 partial fractions. And these 3 partials, you know, they have denominators x, x plus 2, and 3x minus 2. We found the a, b, and c that goes upstairs. A was the -1, b was the half, and c was the 5/2. And so now, in the last step, I'm going to take and integrate term by term, right? So I'll get negative. When I take the first term, I'll get a negative natural log of the absolute value of x. And then the next one, I'll get 1/2 times the natural log of x plus 2. Derivative of the inside is 1, so we don't have to write it or even say it. And then, sorry for jumping ahead here with the 5/6, because isn't that 5/2? And then it's going to be the natural log of 3x minus 2. But then, you know, if I'm thinking about it, don't I have to have a 1/3 out front? Because, you know, if I simply say the natural log of 3x minus 2 and I take that derivative, won't I get 1 over 3x minus 2 times the derivative of that thing, which would be 3? So I've got to have a correction factor, and that's where the 5/6 is coming from. I hope I didn't lose you on the 5/6. So that's a fairly complex example or problem, and I'm going to point you to an example that's in the book. Let's take a look at another one. And this one is more for purposes of exposure. They do show you some stuff with this, and I just need to let you know that it's out there. It's not going to show up on a test or a quiz. It's not even going to show up on the AP test, just because it's pretty involved. But it's very doable, and I want to show you quickly how it's doable. So here it is, right? And we can take and factor this denominator. And we factor it in a particular way. And this is how we think about it. We think about all the terms that would go into this common denominator evenly. So x minus 4 would go into this common denominator evenly. X minus 4 squared would also go in evenly. And finally, x squared plus 3, a quadratic factor, would go in evenly. Now, here is another place where it's a little different. The numerators are always degree 1 less than what I'd call the base of the denominator. And the base is linear, so this is going to be an ax to the 0 or just an a. And the base, although it can be squared, it's a linear factor squared, and so that numerator over that will be a b. But if you have what's called an irreducible quadratic, then the numerator becomes degree 1 less, becomes that cx plus d. So here's where it gets a little complicated. Taking into account all your multiplicities of the linear factor, in this case x minus 4 and x minus 4 squared will both go into it. Gentlemen, if this was a 3 here, then you'd have x minus 4, you'd have an x minus 4 squared, and you'd have an x minus 4 cubed. You'd have 3 of terms related to it, so thank God it's not a 3. But taking this a step further, you know, the left side says x squared minus 5x plus 29 minus 29x plus 5, and the right side, you know, the first denominator goes into the common denominator, Well, it would go in x minus 4 to the first times x squared plus 3 times, and that denominator goes into the common denominator, exactly x squared plus 3 times, and the third denominator goes in exactly to the common denominator, x minus 4 squared times, and then that's multiplied by the cx plus d. Now I wrote it out, but this presents another little challenge here. We're not going to just be able to pick the zeros of the common denominator, because we're not going to get very far with the so-called zeros. There's 4, and then, well, nothing comes out of this one. 4 is a 0, and although that would allow you to solve for the b, it wouldn't allow you to solve for the c, the d, or the a. So what we have to do is something different. We have to take and multiply out this left side, as painful as that is, and we have to multiply that out, which isn't too bad, and then multiply all this out, and then bring together all of our x cubed and all of our x squareds and all of our x's and all of our constants. And then we have to read from the numerator, and we say, there are really 0 x cubed up this numerator, and then there is exactly 1 x squared, and there's negative 29 x's, and there's 5 is my constant. So how many x cubed do I have? Well, I have none of them. And so for my x cubed, I've got a plus c has to be 0, because I end up with no x cubed. And then from the next one, I get that whole thing that I've underlined there in green. I'm going to underline it a second time. How many x squareds do we have? Well, we have exactly 1 x squared. And then we've got this ugly thing. That's how many x's we have, and we've got negative 29 of those, and so that has to equal 3a plus 16c minus 8d. And finally, we've got a constant on the end of 5, and 5 has to equal that expression on the end. So that's how many x cubed, how many x squareds, how many x's, and how many constants, or you might say x to the zeros. Now, I took and put it all in my Inspire and did a reduced row echelon form. I don't know if you did that with your Inspire, putting in that RREF in a matrix. I'm not sure if you're familiar with that, to solve out for what's A, B, C, and D, because this is 4 equations and 4 unknowns, and to do it by hand is just sort of impossible. Well, anyway, after we solve out all of that, we come up to 3 partial fractions, a decomposition of this big boy. And in this last term, there's a common denominator there, so I split the negative x over the denominator, and then the plus 2 over that denominator. And now, using various techniques, this one's going to be the natural log of the denominator. And then this next one, I used a little substitution. Let u equal x minus 4, and then did that deal, back substituted. This next one, let u equal x squared plus 3, then the derivative was 2x dx. I didn't need a 2x dx, only used that, and then this last one worked out to be with an inverse tangent. We could go over how I integrated each one of these terms, but the purpose of this is just to show you the technique to take something ugly, and gentlemen, this is considered ugly, and even uglier if it's not factored for you, and tame it so that we can find the integral. Let's get back on track and do a problem that we'd be expected to do. And I'd like you to see that we have a fraction here, and this is a situation where the degree of the numerator and the denominator are the same. They're both squareds. And this technique will call for doing a little long division. That is to take the denominator into the numerator, and I hope you've done this, where you take the first into the first and you say, well, that goes in exactly one time, and then 1 times, x squared minus 1 would give you the x squared minus 1, and then you would put a subtraction sign and the x squared would drop right, and minus a minus 1 would leave you a plus 1, and maybe in your problems when you did these in the past you'd write the remainder is 1. Well, I don't really like that. You should say technically the remainder is 1 over the divisor. 1, that's the remainder up there, and it's over the divisor x squared minus 1. Because if you take this fraction, and that fraction is it went in 1, and then plus the remainder, and the remainder is 1 over x squared minus 1, and you said, geez, let's find a common denominator, and wouldn't that be x squared minus 1? And you'd say, well, the first term 1 is anything over itself, right? And then if you took that next term and said, okay, that's that, wouldn't the 1 and the minus 1 cancel out, and you'd go right back to this. So the point of all that is we want to take this guy and break it. And then we've got 2 derivatives now, and the first one's quite doable, but this next one is now a little painful. So after the long division, we've got to go off to the side here and say, well, let's take that 1 over x squared minus 1 and factor that denominator. That's our big clue, factorable denominators. And then break off into 2 fractions with each of those 2 denominators. And now as I've gone on with this, I think maybe you're catching on. I hope you are. With thinking about what I've got down here, on the left side with the common denominator, don't I have a 1? And on the right side, if I had brought it back as a common denominator, wouldn't it be up top ax plus 1 over the common denominator, which would reduce to an a over an x minus 1? And then with the common denominator, wouldn't the second denominator go in exactly x minus 1 times, and then wouldn't we take x minus 1 times the b? And then, my little trick, look for the zeros of the denominator. Wouldn't they be 1 and negative 1? So starting with negative 1, the left side is 1. Over here on the right side, if I put negative 1 in, that'll go away, right? And I'll have negative 2 times b, or negative 2b, and b would have to be a negative 1/2. And then if I came back at it one more time and I said, my other zero of the denominator would be a 1, and if I put a 1 in, well, the left side is 1, it's always 1. But if I came over to the right side, wouldn't this one go away this time, and wouldn't I get 2a, and then divide both sides by 2, and I'd get a as a half. So now to finish this off, here it is with partial fractions, right? Don't forget about that first part, right, that I already had, that integral dx, or 1 dx. Maybe I should have put a 1 in there. And then, my a and b, but I've now found what a is and what b is, right? So now I put in my a, and I put in my b. And anyway, isn't this a nice problem now, because the derivative of 1 dx is just x, and then won't this be 1/2 times the natural log of x minus 1, and then won't this be negative 1/2 times the natural log of x plus 1, and we are done. So that's almost 30 minutes. I'm so sorry that this is so long, but I hope this was helpful. See you tomorrow.